Okay, this is lesson 5.4, CAST Rule Part 1, Finding Ratios. We're going to begin this lesson with something called the unit circle. So I'm going to scroll down so you can see the whole thing. This is the unit circle, and the reason it's a unit circle is because every dot on this circle all the way around is exactly 1 unit from the vertex. So this dot, 1 unit from the vertex, 1 unit, 1 unit, 1 unit, which means that this circle has a radius of 1. That's the unit circle. The unit circle can be drawn on the Cartesian plane with x's and y axes, and we can define angles on the unit circle, and we can look at ratios. Let's draw some angles in each of the quadrants and talk about some specific relationships. So let's start with an angle in the first quadrant. Well, an angle in the first quadrant, I'm just going to pick one of these dots. Let's say this one. And I'm going to create an angle. From standard position, and we're going to call it theta. We talked in the last lesson about how in the first quadrant, theta and beta are equivalent. The related acute angle and the angle from standard position are the same angle, because remember, related acute angle goes from terminal arm to initial arm, from terminal arm to x-axis, and in this case it's in the same quadrant as the initial arm. So in quadrant 1, theta is beta. And if I were to draw on the 3 sides of a triangle that create this angle, I could drop a side here and draw a side along the Cartesian plane, and what that does is it creates a right angle in the first quadrant and allows us to define our angle. Well, what do we know? Well, on here we would have a point x and y. The y would be how vertical it is from the origin or from the x-axis. So this side of our triangle would be a y. The x of this point would be how far from the origin we are on a horizontal, which would make this side of the triangle our x. And this part, or the hypotenuse of the triangle, is actually the radius of our circle. So we have an x, a y, and an r side of our triangle on the Cartesian plane. And if we were to take sine of our angle, we would get opposite y over hypotenuse r. Y over r. And this is a new definition of sine. Y over r. Instead of opposite over hypotenuse, if we're talking about a point on the unit circle, or a point on the circle as it rotates from standard position, we can talk about y and r. We can do cosine the same way. Instead of y over r, that would be adjacent over hypotenuse, x over r. And if we were talking about tan, tan would be opposite over adjacent. Y over x. And if you notice that if this point is in the first quadrant, the x and y would be positive. So the sine, cos, and tan ratios, positive divided by positive, positive divided by positive, positive divided by positive, you'd always get a positive. All the ratios are positive. If we draw an angle in the second quadrant, some things change. I'm going to draw a terminal arm up here. Let's call this our theta. I'm going to call it theta 2 now because we're in the second quadrant, which would make our beta right here. And if we drop our vertical line and we draw across the Cartesian plane, we can create a nice right angle triangle in the second quadrant. And if we define this point as an x and a y, we have to be a little bit careful. Because we're in the second quadrant, the x's in this quadrant are negative. Since we're going up, though, the y's are still positive. So we've got a negative x and a positive y. So if I go to label my triangle, well, I've got a y, vertical, and I've got a negative x. the radius will still be positive. The radius of this circle is always going to be 1, positive 1 in fact, or anything if we scale it up from a single unit. But in this case, r, still positive. And if I go to do my sine, cos, and tan, well, something changes a little bit. Let's draw. So we got an angle in this quadrant which creates this triangle. And if I go to take sine of my theta 2, I get opposite over hypotenuse. I still get y over r, which is the same as the first quadrant. The differences come when you go to take tan and cosine. Let's do cosine. If I take cos of theta 2, I get adjacent over hypotenuse. And I get negative over a positive, which creates a negative ratio. If I do tan, I get opposite over adjacent. And that creates another negative ratio. In the second quadrant, the only ratio that's positive is sine. Sine is positive. The angle relationship between theta and beta is that theta is 180 degrees, that would be a whole rotation, minus whatever we fall up short, in that case beta. So in the second quadrant we still have angle relationships sine, cos, and tan, but notice this time we have some negatives introduced to our ratios, which change the sign. Now there's a direct relationship between sine of beta and sine of theta, and the relationship is that you'll always get the same ratio. The only difference is the sign of that ratio, the SIGN sign of that ratio, and that sometimes it's positive and sometimes it's negative, and it depends on what quadrant you're in, because the x and y coordinates in those quadrants can either be positive or negative. We're going to keep looking at this relationship in class, but I need you to kind of see it for the first time today. In fact, we're not actually even going to finish the ratios in quadrant 3 and quadrant 4. The only thing I'm going to tell you is that in quadrant 3, the relationship between theta and beta is that theta is 180 degrees plus beta. And in quadrant 4, the relationship between theta and beta is 360 degrees minus beta. Very similar to the relationships that we did in the last lesson, except I was writing them in terms of beta. We can just rearrange and solve for theta. In the second quadrant, the ratio that was positive was sine. In the third quadrant, both x and y will be negative, because this point down here would be negative for x's and negative for y's. And the only ratio that would end up coming out positive of that is tan. And if you look, it's because y negative divided by x negative would give you a positive. So in the third quadrant, tan is positive. And in the last quadrant, well, we've got an all positive, a sine positive, a tan positive. I bet you might be able to guess which one's positive, and it's cosine. And the reason cosine is positive in this quadrant is because, well, if we go to take a point, let's say this point right here, the x would be positive because we'd be on the positive x arm, and the y would be negative. And if we go look at our ratios and we make the y negative, this ratio would be negative and this ratio would be negative. The only one that would be positive is the one that doesn't have y in it, which is cosine. Okay, what we end up with is ASTC, or if we start in quadrant 4 and count all the way around, CAST. This lesson is called the CAST rule lesson because in this lesson you're going to see that the ratios will always come out positive or negative as dictated by what quadrant they're in. If you're looking for sine, cos, and tan ratios in the third quadrant, the only one that's going to come out positive is tan. In the fourth quadrant, the only one that's going to come out positive is cosine. In the first quadrant, all of them are going to come out positive, and in the second quadrant, only sine is going to come out positive. And you got a sneak preview as to why in the first two quadrants. And as we continue to work through this lesson, And in class, we're going to expand on this idea. But for now, that's a brief introduction. If we scroll down, I'm going to show you how to find the exact values for each of the following trig ratios. So we've got an angle. We don't know what the angle is, but we know it takes us into the third quadrant. And P is the point, negative 15, negative 8, that gets us to this spot on the Cartesian plane. Now, if I draw my vertical up to the axis, I can create a nice right angle triangle. And since this is the y, the vertical, and this is the x, the horizontal, we can assign the x to our horizontal and the y to our vertical. And since we're in the third quadrant, you can see that x and y are both negative in this quadrant. The question asks us to find the exact value for the 6 trig ratios: sine, cos, tan, secant, cosecant, and cotan. We could do that if we knew what r was, if we knew what the radius or what the hypotenuse side is. And we can find the hypotenuse side using the Pythagorean theorem, a squared plus b squared equals c squared. If we use the labels x, y, and r, it would be x squared plus y squared equals r squared. If you want to use a, b, and c, that's still fine. And here's a little bit of math to support the idea that I said in the last part that the radius is always positive. Here's some math to support that. If I take my x, negative 15, and square it, that number is going to come out positive. And if I take my negative 8 and square it, that number is also going to come out positive. Positive and positive. Negative 15 squared plus negative 8 squared gives me 289. Negative 15 squared is 225, and negative 8 squared is 64. Adding together, you get 289. And now if we want to solve for r, we would square root both sides. And r would be 17. And in this case, it works out to a nice number. And positive 17 it works out to, in fact. And now we can find the exact ratios. What's interesting is that the ratios for theta are defined by the triangle. That's this little triangle with the acute angle beta in there. And there's always a direct relationship between sine, cos, and tan, and any trig ratio of beta, the related acute angle, and theta, the angle from standard position. And the relationship is that you will always get the exact same value of sine, cos, and tan. The sine, the SIGN, is the only thing that will vary. And the sine is dictated by what quadrant you're in. Using the sides of the triangle labeled with the correct signs will ensure that you get the right answer. And this is something that I'm going to explain more in class. So make sure you're in class tomorrow. Sine theta is defined in this triangle by the y over r, or the opposite over hypotenuse, keeping in mind that the opposite is negative 8. The sign is very important, negative 8 over 17. Cosine would be adjacent over hypotenuse, negative 15 over 17. And tan would be opposite over adjacent. Two negatives make a positive, so I'm going to rewrite this. Two equal signs on the same lines, not great, but for the sake of space, I'm going to do it. Look at which one ended up positive. Tan. And if we go up to our investigation on the unit circle, we'll see that in quadrant 3, the only ratio that should end up positive is tan. The only primary ratio. When we take our reciprocals, we should end up with another positive one. Do you remember your reciprocals? The reciprocal of sine is cosecant. And if we flip this fraction, we get 17 over negative 8. And we're just going to rewrite that as negative 17 over 8. The negative is assigned to the bottom, but I'm going to rewrite it in front. And secant would be 17 over negative 15, which is negative 17 over 15. And cotan would be negative 15 over negative 8, which two negatives make a positive, 15 over 8. So cotan is also positive, but our cast rule is only defining the principal, or the primary trig ratios, not the secondary ones as well. But if you look, tan is the one that's positive, and it's supported by the idea that in quadrant 3, tan will always be positive. All right. If you flip the page over, here's a second question that's just like the first question that we just did. What I want to show you in this example is, well, basically the exact same skills from before, but I want you to try it on your own. We're going to draw the diagram together, but you're going to finish the question. So to draw the diagram, we're going to draw the Cartesian plane. And we're going to plot the point negative 8, 6. Negative 8 would be on the negative x scale, and 6 would be positive. So I'm going to approximate where it is. And I'm going to draw the terminal arm to the vertex. And I'm going to draw my angle from standard position. And there's our terminal arm. The coordinates of the point is on the terminal arm. So that point is on the terminal arm of an angle from standard position. There's my theta. The related acute angle would be the little angle inside. And if I drop my vertical down, I've got a nice right angle triangle. And since my coordinates are negative 8 and 6, negative 8 goes on the x-axis, and 6 goes on the y. Now we have a diagram drawn. Just like on the last page, I want you to try this question for yourself, modeled just like example 1. So you can either pause the video now, or you can keep going, finish the next example, and then try it after the lesson. All right, how does all of this connect? Well, here's how it connects. Determining the exact value of an angle. Sorry, the exact values using an angle from standard position. Well, we're going to look to find sine of 225 degrees, cotan of 210 degrees, and cosine of negative 30 degrees. And the way we're going to do it is by using the Cartesian plane and our knowledge of special angles, using the special triangles, and the cast rule. Let's try an example together. The first step is to draw the diagram of the angle on the Cartesian plane. Our angle is 225 degrees. So I'm going to draw my Cartesian plane. I'm going to consider what quadrant 225 would be in. It would be in the third quadrant. So I'm going to draw a terminal arm. And I'm going to draw my theta. To evaluate and figure out what sine of 225 are, we need an opposite and a hypotenuse. So we need a triangle. And we can create a triangle in this third quadrant using my reference angle, which we're not sure of what it is yet, but we're going to find it. So I'm going to draw my triangle by dropping a vertical to the x-axis, including the right angle. We don't know any of the sides, but what we do know is that our related acute angle would be, well, if theta is 225 and we rotated past 180 degrees a little bit, how much? Well, that would be what beta is. So to find beta, we do 225 minus 180. It's how much further than 180 did we go? And the answer is 45 degrees. And 45 degrees is a significant number. How come? 45 degrees is one of our special triangle angles. Which special triangle? Well, I'm going to draw it. It's the 45, 45, 90 special triangle. And if you ever see a question that says find the exact value, the related acute angle is always going to be one of those special triangles. And in this special triangle, the sides are 1, 1, root 2. And if we were asked to find sine of 45, this question would be pretty easy. We would just do opposite over hypotenuse and get 1 over root 2. But that's not the answer, because we're not asked to find sine of 45. We're asked to find sine of 225. And according to the cast rule, the only ratio that should be positive in this quadrant is tan. So sine of 225 can't possibly be 1 over root 2. But it is related to 1 over root 2, and here's how. Let's look at our triangle again, and since we're drawn in this quadrant, and we have a related acute angle of 45, we can label this with 1, 1, root 2, but we have to be careful about the signs of these sides. So let's for a second consider what quadrant we're in. We're in quadrant 3. The y is down, so the y should be negative. And the x is to the left, so the x should be negative too. X and y are both negative in quadrant 3. So if I want to find sine of 225, I would use my triangle drawn in the third quadrant with the appropriately labeled sides. And now we can do it. Opposite, negative 1 over hypotenuse, root 2, or y over r. Negative 1 over root 2. And if I want to rationalize my denominator, I multiply top and bottom by root 2. I get negative root 2 over root 2 times root 2, 2. So what happened here? Well, let's debrief. We got a preview of what the answer was going to be from our special triangle. Opposite over hypotenuse, 1 over root 2. It was almost 1 over root 2. That's the correct ratio. The ratio from the special triangle or from the related acute angle will always be the same as the principal angle. That's how they're related. The related acute angle and the principal angle are related in the fact that they'll give you the same ratio. The only difference is the sign, the SIGN sign. And that comes from the cast rule. Cast rule says, remember what quadrant you're in and label the sides, negative and negative for x and y. Now when we do opposite over hypotenuse, we get negative 1 over root 2. There's this very important relationship that we need to understand here. And it's that when you take the sine, cos, or tan of beta, you're going to get the exact same number as if you did sine of theta. However, the value that you get from sine theta and sine beta will be the same. The SIGN sign of that ratio may be different depending on what quadrant you draw it in. So that's why I put the absolute value bars. Okay? If you're in the first quadrant, you'll get the exact same answers. And according to cast rule, if you're in the second quadrant, you'll get the exact same answers as well. But if you're in the third and fourth quadrant, the SIGN of our ratio would be negative. All right, I'm going to do one more example, cotan 210, and see how we do. All right, let's draw our angle from standard position, 210 degrees. $210 again would take us into the third quadrant. How far into the third quadrant? Well, maybe we're starting to get good at this. I don't know. But we're over 180 degrees by 30 degrees. So the special triangle in this case would be the 30, 60, 90 special triangle. Beta would be 210 minus 180. That's how we get our 30. So let's draw that special triangle. You'll have it on your formula sheet. And it's the 1, 2, root 3 special triangle. And if we go and label our sides or our triangle with the 1, 2, and root 3, we have to be careful. Based on the way I drew this, we might mistakenly put the root 3 here. The 1 should be the side across from the 30. So across from the 30 should be the 1. Across from the 60 should be the root 3. And across from the 90 should be the 2. And now we have to consider the signs. Negative and negative. X and Y are negative in this quadrant. So now that we have a perfectly labeled diagram, we can find cotan 210. Cotan 210 should be the same as 1 over tan 210, which would be 1 over opposite over adjacent. -1 over -√3. Whew. How do you divide a fraction? Well, you flip it and multiply. 1 times -√3 over -1. Negatives make positive. Divide by 1 is just the number on top. Multiply by 1 is just the number on top. We end up with just √3. Cotan 210 is √3. And let's see if we're right. In the third quadrant, according to the CAST rule, C-A-S-T, maybe I should have labeled that. C-A-S-T. There's my T, there's my S, C, sorry, A and C. CAST rule. T, in this quadrant, tan should be positive. Well, negative divided by a negative is in fact a positive, and we did use the tan ratio. So cotan should also be positive. We got a positive answer. We probably did it right. I'm going to get you to try the third example on your own. Now don't be intimidated by the negative angle. Just draw the angle counterclockwise and make sure you understand that it's in quadrant 4. And then the question should be very similar to the two we've done before. You can check your answer on the course website. And that's it for part 1 of the CAST rule. This is one of the most challenging topics that we'll do this year. And I know I've said that before, but it's true about this topic. It's very, very important that in class tomorrow we're practicing this concept, doing the warm-up, doing the practice questions, and asking for help. The journal is also based on this topic. So we're going to assign the journal, and hopefully by the end of the 2 lessons and the journal activity, we've got a solid understanding of the concepts in this video. At a very minimum, hopefully you've now seen it, so that when I explain it to you again in class tomorrow, it will start to make more sense. That's it for lesson 5.4, part 2. Thanks for watching, and I'll see you next time.